Hi, everyone, and welcome back. This is part 2 of the sum and difference formula video for trigonometry. So we'll pick up where we left off at the last video. We did the first 4 problems. The last couple of problems we did, to finish up the previous video, I think if I remember right, oh, what happened to my slide? There it is. If I remember right, we did the sine of 105 degrees. And then we did the sine of 75 degrees. And the way we did these was we said, okay, well, we have those special angles on the unit circle, those multiples of 30 and multiples of 45 degrees. So we could take 105 and write that in terms of some of those special angles. So 105, 60 plus 45. And 75 degrees, we could say, is 45 plus 30, right? And then we used this guy down here, the sine of alpha plus beta. All right, so this is a similar problem. It's going to be a little bit more evolved, but not terrible. All right, so let's free up some space here. Now we have an angle in radians, not degrees. Right, the last couple of problems were in degrees, 105 degrees, 75 degrees. Now we have 5 pi over 12 radians. But same issue. 5 pi over 12, and that's somewhere in quadrant 1. Well, that's not one of those special angles where we know the terminal point. We know pi over 6. We know pi over 4. We know pi over 3, pi over 2, but we don't know pi over 12, 5 pi over 12. So what we got to do is see what we could do. We got to play around with this number. I'm going to leave off the pi for a moment. Just say, look at the fraction 5 over 12. Well, how can we split up the number 5? Well, 5 is 1 plus 4. So 1 over 12 plus 4 over 12. And that works here. 4 over 12 is a third, right? So pi over 3, that's on our unit circle, but 1 over 12 is not. So that's not going to work. 5 is also 3 plus 2. So 3 over 12 plus 2 over 12. All right, so 5 over 12. Okay, 3 over 12 plus 2 over 12. There's a pi in there, so it's actually 5 pi over 12. So that's 3 pi over 12 and 2 pi over 12. Well, what is 3 pi over 12? Well, that fraction reduces. 3 over 12 reduces to 1 over 4. So that's pi over 4. And then if we look at the 2 pi over 12, 2 over 12 reduces to 1 over 6. So that's pi over 6. All right, so 5 pi over 12 can be written as 2 of those special angles. Specifically, the sum of 2 of those special angles, pi over 4 and pi over 6. So it looks like if we want to take the tangent of 5 pi over 12, we can take the tangent of the sum. And down here, we have a formula that looks just like that. Tangent of alpha plus beta. All right, so let's say the tangent of 5 pi over 12. Well, that's the same as the tangent of pi over 4 plus pi over 6. Now you could say pi over 6 plus pi over 4. Either way works. Okay, so in our formula, alpha is the pi over 4, and beta is the other angle, the pi over 6. Right? And these are going whoop, right into this guy. So if we apply that formula, tangent of the first plus tangent of the second divided by 1 minus tangent of the first times tangent of the second. So let's just replace the alpha and the beta in the formula with the angles pi over 4 and pi over 6. Okay, so this is the tangent of pi over 4 plus the tangent of pi over 6. And then we've got over 1 minus the tangent of pi over 4 times the tangent of pi over 6. All right, we got to do some evaluating and simplifying. It shouldn't be too bad because this guy right here, tangent of pi over 4, there's another one down here, again, tangent of pi over 4. Well, that's equal to 1. Tangent of pi over 4 is 1. All right, so we're taking this from, well, from wherever you get your values, whether it's looking at a unit circle or you have them memorized. Either way, tangent of pi over 4 is 1, and the tangent of pi over 6, it's not as convenient as a number as 1, but it is what it is, square root of 3 over 3. Okay, so that's tangent of pi over 4, 1, plus tangent of pi over 6, root 3 over 3, divided by 1 minus tangent of pi over 4, which is 1, times the tangent of pi over 6, which again is root 3 over 3. So now we have to simplify. We got to do some simplifying. We have fractions inside of fractions, and it's just a mess, right? So let's see what we could do. Well, anytime you've got fractions divided by fractions, you want to think in terms of just the way we divide fractions, right? If you've got a fraction divided by another fraction, right? One fraction on top, one fraction on the bottom. We don't have that. We have two terms here. So we're not there yet. But if we have one fraction on top and one fraction on the bottom, that's all we got. Well, keep, change, flip, right? Dividing by C over D means multiplying by the reciprocal D over C. All right, so this is how we divide fractions. Maybe you've heard keep, change, flip. You keep the first fraction, you change the division into multiplication, and then you flip the second fraction. All right, I'm going to go to the next slide. We're definitely going to need some more room here. So I'm just going to copy this over. We had 1 plus root 3 over 3 divided by 1 minus root 3 over 3. Well, we're going to need to get a common denominator. So we're going to treat that number 1 like it's a fraction, 1 over 1 plus root 3 over 3. So we'll combine those two fractions into 1. On the bottom, we've got a 1 minus, so let's say 1 over 1 minus root 3 over 3. To add or subtract fractions, we need a common denominator, so we could multiply that 1 over 1 by 3 over 3. That will give us a common denominator. I'm going to show all of the steps here, not take anything for granted. So that's 3 over 3 plus root 3 over 3 on top. No, we're ready to combine those. Sorry, let's put those together into one fraction. 3 plus the square root of 3 over 3, right? We have a common denominator of 3, combine across the top. On the bottom, we've got 3 minus the square root of 3, all divided by 3. Let's bring it down here. Keep, change, flip. So top fraction. Times the reciprocal of the bottom fraction. So those 3's cancel. 3 on top, 3 on the bottom. Now we've got 3 plus the square root of 3 divided by 3 minus the square root of 3. Okay, we're not there yet. All right, we have a problem. Right here, this is a problem. In order for this fraction to be considered simplified, one, we have to remove any common factors between the top and the bottom, but more, relevant here, we can't have square roots on the bottom. We can't have square roots on the bottom. So that process for removing square roots from the denominator of a fraction, this is called rationalizing. If you go about 25 videos back in this playlist, we did a video on rationalizing denominators. Now, the way we do that, it may have been a while, so this could be a good refresher. The way we do that is we multiply. We want to get rid of that square root of 3 on the bottom. That's our focus, that square root of 3. So what we do is we multiply by the conjugate. Right? The bottom is 3 minus, the conjugate is 3 plus. Right, so 3 plus the square root of 3. We multiply by the conjugate of the denominator, the conjugate of the bottom. Whatever you do to the bottom, you got to do to the top. 3 plus the square root of 3. Right? Got a FOIL. Right, we got 2 terms times 2 terms. So let's throw in some parentheses just so it visually is making more sense. Right? We have to multiply each term in the blue parentheses by each term in the red parentheses. So we FOIL that out. First, outer, inner, last. All right, so we're going to get a fraction. We have to multiply out the top. We have to multiply out the bottom. On top, first times first. 3 times 3 is 9. So let's do it this way. First times first. 3 times 3 is 9. Outer times outer. 3 times the square root of 3. So that's 3 root 3. FOIL. I is inner. Inner times inner. Again, 3 times the square root of 3. And then last times last. Square root of 3 times square root of 3 is the square root of 9, which is 3. We'll do the same thing on the bottom. First times first. 3 times 3 is 9. Outer times outer. 3 times the square root of 3 is plus 3 radical 3. Inner times inner. Well, now there's a negative sign. Right? So that's minus 3 radical 3. And last times last, negative times positive is negative. Square root of 3 times square root of 3, square root of 9, or 3. Okay. So collect like terms. That and that, they go together. That's 12. 9 and 3 is 12. This and this, like terms. 3 root 3, 3 root 3, that's a total of 6 root 3. All right, so on top of the fraction, we've got a 12 plus 6 times the square root of 3. On the bottom of the fraction, now this is why we use the conjugate. We have a positive 3 root 3. We have a negative 3 root 3. They cancel. Thus, there is no square root in the denominator, right? The multiplying by the conjugate eliminates the square root. And then we've got a 9 minus 3, which is 6. We are almost done. We're almost done. It looks like we could factor out a 6 on top. We better be close because I'm running out of room down here in the corner. If we factor out a 6 on top, we're left with 2 plus the square root of 3. And it looks like those 6's cancel nicely. Boom, boom. And we are, with very little room to spare, we've got 2 plus the square root of 3. Whew. So I'll go ahead and circle that. Let me go back to the first slide, the previous slide where this problem started, right? We use the formula for the tangent of the sum of two angles. It's not the only way to do this problem. Right, we're going to look in the very next video, we could do this problem again. This video covered the sum and difference formulas. In the next video, I'm going to talk about what's called the double angle and the half angle formulas. It turns out we could have used one of those for this. I don't think it would have been any simpler or more succinct of a solution, but this is one way to solve the problem. Not the only way. And for those of you, if you want to just a brief glimpse ahead, what we're going to do next, the tangent of half of one angle. The tangent of half of an angle. Now, if that theta, right, let me just make that red. If this theta right here was one of those special angles that we are familiar with, let's say, for example, that was pi over 6. Let's say that was 5 pi over 6. 5 pi over 6. Well, then we would get half of 5 pi over 6. And what is half of 5 pi over 6? Well, that is precisely 5 pi over 12, right? Which is what we just did. This right here is the tangent of 5 pi over 12. We use the sum and difference formula, well, because I haven't covered yet the half angle formula, but we could have definitely used the half angle formula, and we might maybe I'll just do this problem again in the next video. Anyway, we have one more problem to do before we call it quits, and this one's a little bit different. Verify the identity. Remember, these problems verify the identity we treat this equal sign like it is a question mark. So we want to start with cosine of x minus pi over 2. And we want to connect it to sine of x. We want to show these two are equal. And we do that by saying, well, we could show cosine is equal to this thing. And then this thing is equal to that thing. And that thing is equal to this other thing. And this other thing is equal to sine. So if we could connect the two by this sort of this string of logical connections, then we would have shown why it is such that the cosine of x minus pi over 2 is indeed equal to the sine of x. All right, so let's see what we got. The cosine of x minus pi over 2. Well, that is equal to, this is the difference formula for cosine. Cosine of alpha minus beta, cosine of something minus something, right? Cosine of the first times cosine of the second minus sine of the first times sine of the second. Let's see, is this going to work? What is the cosine of pi over 2? What is the cosine of pi over 2? Now that is equal to 0. So the cosine of x times the cosine of pi over 2, that whole thing is gone. Oh, sorry, I'm using the wrong, made a small mistake there. Don't make sure we're using the right formula. Cosine, cosine plus sine, sine. If we start with a minus, the formula uses a plus. So cosine of x times cosine of pi over 2 is 0, plus sine of x times sine of pi over 2. What is the sine of pi over 2? Well, that is equal to 1. So we get the cosine of x times 0 plus the sine of x times 1. One times anything is itself. So this is the sine of x. Pretty straightforward. Once we apply the formula, it falls right into place in just 1 or 2 steps. Again, these verify the identity problems. They do get much more complicated. This one was a pretty straightforward one as far as these verify problems go. Okay, so that's it for this video. In the next few videos, I'm going to do basically what we just did. Look at one type of formula. We just looked at the sum and difference formulas. Next, I want to talk about the double angle formulas. And then I want to talk about the power reducing formulas. And then I want to talk about the half angle formulas, and we'll go from there. All right, so that is it for this video. I'll see you on the next one. I hope this was helpful.